Hello and welcome to the next session of your final exam review from CDLI for Calculus 3208. In this session today we're going to be looking at limits and continuity again, and our specific topic this time we're going to talk about infinite limits and non-existent limits. So those are different from limits at infinity. Infinite limits are what happens if the function itself is approaching infinity, negative infinity, or a discrepancy, and we'll get into all those details shortly. So let's get started. Excuse me. So first thing we're going to see are infinite and non-existent limits. So infinite limits are our first topic, and then we'll talk about non-existent, and then we're going to look at all that stuff graphically, and then finally we'll look at a strategy for evaluating infinite and non-existent limits from an algebraic expression. So let's get right down to business with that. So we'll start with an example that's been sort of already pre-done for us, and we'll just talk about the details here. So for this particular function that we're given, f of x is equal to x minus 3 all squared. And we're going to look at some tables of values for this function and a graph for this function and talk about its limit as x approaches 3. So as x approaches 3 here, we can look at the first table of values that's been created. And in this first table, we're getting values of x that get really close to 3 coming from the left, or slightly less than 3. And for those, what we see is that the value of f of x is growing and growing, getting really, really large. In fact, when we get at 2.999, the value that we get for f of x is 1,000,000. And if we come from the right-hand side, the values of x are getting smaller to get closer to 3. And as we do that, we can see the values of f of x are the same as those we had in the other table for the corresponding points on the other side of 3. And they're also getting really large and staying really positive. So on the graph, what that means is as we get close to 3 from the left, the values of the function are growing infinitely toward positive infinity, and it's the same story coming towards 3 from the right. We're growing infinitely toward positive infinity. So we look at the limits. The limit from the left and the limit from the right for this particular function are the same thing. They're both equal to positive infinity. So all we have to say here, because of that behavior, is we say that the limit does in fact exist. So we say that the limit exists in this case, and we're going to say the limit as x approaches 3 of our function 1 over x minus 3 squared is equal to positive infinity. Now it sounds a little bit contradictory when we say it in our regular old English language that there's an infinite limit. That doesn't even make sense really in terms of our everyday language. But mathematically speaking, we do that because we want to differentiate between this type of infinite behavior and a different type that we'll see shortly. So let's look at sort of just the exact opposite of this one. Let's take the function that looks the same as the last one, only we're going to add this negative sign right in here. So we're going to say negative of the same function we had 1 over x minus 3 all squared. And then we'll take a look at the tables of values. So for all those same x values we had from the last time, the example we have here will have the same y values except that they're all negatives. So whether we come from the left or right, we know that all that's going to really change is just the sign on those values. So if we look carefully at the graph, approaching positive 3 from the left, what's happening is our y values are trailing off to negative infinity downward, and the same thing as we approach from the right. So if we look at the limit statement up here, approaching from the left, we're heading toward negative infinity, and approaching from the right, we're also heading toward negative infinity. So even though negative infinity is something that we don't normally think as being limited, we do say here that the limit of this function as x approaches 3 of negative 1 over x minus 3 squared, like so, does exist. We say that it equals negative infinity. Strange but true facts. All right, let's take a look at why we have to have these limits that equal infinity. And it's because we want to distinguish those type of behaviors from the type of behavior we get for non-existent limits that are also infinite discontinuities. So if we look at this particular function we have this time, it's 1 over x minus 3. So no square here, it's just 1 over x minus 3. And if we look at the x values coming from the left toward 3, the values of x get larger and larger, but stay restricted. They're allowed to approach a value of 3, and we can say by filling those into our equation, the y values we get really big but really negative, so up to negative 1,000 there. And coming from the other side, the values of x get really close to positive 3, but they're always at least slightly bigger than it. And the y values that correspond to those for this particular function also get really large, and they approach really big numbers. So graphically, coming toward 3 for x from the left side, we can see that y is going to trail off to negative infinity. And coming toward 3 from the right, we can see that y is going to zip way up to positive infinity there. So using our limit notation, we say that the limit as x approaches 3 from the left is negative infinity, but which is not equal to in this case. So that not equal to right there is a big deal for us. And we look at the limit as x approaches 3 from the right, that one is positive infinity. So they're not the same. So in this case, we can't say that we have a limit that's equal to infinity because the limits don't agree from left and right. And therefore, we know by definition here that we can say the limit as x approaches 3, if those limits don't agree for our function 1 over x minus 3, what we say is that that limit does not exist. Or abbreviated form, we can just say DNEUSA quickly. So that limit does not exist at all. Alrighty, let's look at some examples now. So in this case, what we're given is 3 graphs, and for each of these graphs, we have to figure out the limits from the left and right as x approaches some value that we're calling a, and then the overall limit as x approaches a. It's again a little bit unclear on this slide, but right here, this should be x approaches a from the right, so there should be a plus sign there. And I think you're going to have the same thing. Yeah, we should point it out down here as well. These should be plus signs. It doesn't translate very well from the original slide into this format, but that's okay. We can fix it real quick just like this, and then we're all on the same page. Okay, so looking at the first function, if we approach a from the left, this function goes upward toward positive infinity, approaching a from the right, upward toward positive infinity. So what that tells me is that the limit as x approaches a from the left is here at positive infinity. So is the limit as we approach from the right. And since they agree, we do have a limit at positive infinity as x approaches a. So for the next one, we can see that whichever side we come from the left going downward to negative infinity as we get close to a, and from the right going downward to negative infinity as we get close to a. So in either case here, we can see that the limit as x approaches a from the left is negative infinity, and it's the same thing from the right. So overall, we have a limit of negative infinity. Okay, and in the last example, coming from the left, as x approaches a, we're going upward toward positive infinity as we approach that asymptote, and coming from the right, we're going downward toward negative infinity as we approach that asymptote. So from the left here, our limit is positive infinity, and from the right, our limit is negative infinity. But since they don't agree, we have to say that the overall limit, DNE, does not exist. So the limit here does not exist, and we're in good shape. So we've got all that straightened out. Alrighty, so that's all well and good. It's fairly straightforward and simple to see that from a graph. But what if we're given examples like these, where we have to determine those limits just from an equation? Well, you could sketch the graph, but it's not the most efficient way to go about this. One thing we can do is just examine those left and right-hand limits algebraically. So let's look at what happens to this particular function in part A as x approaches 3, first of all, from the left. And we'll look at all 3 factors that this one has been broken into to determine what happens to all of those. Oops, that first one should be an x minus 2, excuse me. And then we're all over x minus 3 here. So as x approaches 3 from the left, x minus 2 is going to approach, for this part, a value of positive 1, because 3 minus 2 will give us 1. We're going to get really close to that. And whether we come from the left or the right, those values are still going to be approaching 1. And for the second factor, as x approaches 3 from the left, and it doesn't matter whether we come from the left or the right, if we fill in 3 there, we're going to be approaching a value of 4. So we can kind of think of this, although it's not really equal to this yet, but we're just going to say that to help us figure it out. The limit as x approaches 3 from the left here, well, the numerator at least is approaching a finite value of 4. Let's look at what happens to the denominator now. Well, this is where it gets tricky, because as we're going to approach 3 here, we're going to get a value of 0. So this is going to approach 0. However, I can't divide 4 by 0. So how do I figure out if I'm going to positive or negative infinity? Well, if we're approaching 3 from the left, let's think about x minus 3 for a second. X minus 3. If I fill in a value for x that's getting close to 3, but from the left it's got to be less than 3. So let's say, for example, 2.9 minus 3. That's going to give us a value of negative 0.1. And if I use 2.99, I'll get negative 0.01. But the moral of the story is, as we approach from the left, the number on the left here is always going to be less than 3. So this one will always be less than 3, giving us negative values. So we are approaching 0, but we say that we're approaching 0 through negatives. And we indicate that by putting a little negative with no number, but just a negative exponent on the 0. So what that means is that 4 divided by numbers that are getting close to 0 will get infinitely large, but since 4 is positive and we're approaching 0 through negatives, we say that this is approaching negative infinity. All right, so staying with example A here, let's look at what happens if we approach 3 again for x, but we're going to approach from the right. So this time we're going to take x minus 2 times x plus 1. And there's not much new story to tell in the numerator, because whether we approach from the left or the right, 3 minus 2 is still going to give us a value of 1. 3 plus 1 will still go to 4. So over here we're still going to approach 4. In the denominator this time though, if we look carefully at this, this is going to give us a value of 0. So we're going to end up with something that's approaching 0 in the denominator. So if we approach 0 in that denominator, let's choose an example. So if we're approaching 3 from the right, let's take a number like 3.1. So if I take 3.1 subtract 3, I get a value of positive 0.1. And no matter how close I make this to 3, as long as I'm approaching from the right and those numbers are slightly bigger than 3, I know that I'm going to approach 0, but it's going to be through positive numbers. So I'm going to get 4 divided by numbers that are getting really, really, really small, but staying positive. So what happens is the overall value of that fraction gets really big, and it approaches positive infinity. So for our first example here, since we approach negative infinity from the left, positive infinity from the right, we would say for the first one that the limit does not exist. Okay? So that's our story on that first example. Let's take a look at the second one now. For the second example here, what we're going to do, I'm just going to delete this stuff out of our way so we have some space to work. Let's get rid of this business over here as well, so that's gone. All right, so let's talk about the second example now. And we'll take the same kind of approach. We'll forget about this guy that we've already got finished. So we're going to look at the limit as x approaches to, first of all, from the left, of x plus 1 over x minus 2 to the power of 4. And then we'll look at the limit as x approaches to, from the right, of x plus 1 over x minus 2 to the power of 4. Okay, so in either case, as we approach 2, x plus 1 is going to approach a value of 3. And that's going to be true for both sides here. It doesn't matter whether we come from the left or the right. So we're going to end up with a fraction whose numerator is approaching 3 and whose denominator is going to approach, well, let's have a look. From the left, this is definitely going to approach 0. And what I'm going to point out here is that you notice that the exponent we have is 4. So it doesn't matter whether the stuff inside those brackets down here is going to approach 0 from the left or the right. If I raise it to an even-powered exponent, I'm always going to get a positive number. So overall, all of this stuff in my denominator down here is going to approach 0, but because of my even-powered exponent, we're going to approach 0 from the right, and it doesn't matter what goes inside there. As long as we're approaching 0, raising it to the power of 4 will always give us 0 through positive numbers. So in both of these cases, we're approaching positive infinity. And if we're approaching positive infinity, then overall this limit does exist, and it's equal to infinity. Okay? Let's jump on now and look at some test type examples. So here's one, and it says, what is the value of the limit as x approaches 1 from the left? So we're only looking at approaching from the left here of that particular function. So let's see what happens. In the numerator, as we approach 1 from the left, we're going to get 2 times 1 minus 3. So that approaches a negative 1. So we're going to have stuff approaching negative 1 on top. And on the bottom, as we approach 1, this business is approaching 0. But if we're approaching 1 from the left, is this going to be approaching 0 through negatives or positives? Well, let's just pick a test point and check it out. So a number that's close to 1, but to the left of 1, could be something like 0.9. And if I fill that in there, that's going to give me negative 0.1. So what we're doing here is we're approaching 0, but through negative numbers. So if this is approaching 0 through negatives, the top of the fraction is negative and it's constant. The bottom is shrinking to 0 and it's staying negative. So overall, this is going to get really big, and a negative divided by a negative gives us a positive. So we're actually approaching positive infinity for that particular example. All right, so I hope that's a good enough explanation for you. So here's a your turn question, and on this your turn question, you're asked to evaluate each of those limits that are given. One of them is a limit as x approaches 4 from the right, so this here should be, we're approaching 4 from the right-hand side. So that's really what should be down in here. So just to clarify, in case that's not easy enough for you to see right there, that's approaching, that should be actually negative 4 from the right, excuse me. So what we're approaching there is negative 4 from the right-hand side. So make sure that's clear. And this second limit, we're just looking for the overall limit as x approaches 2 for this one. So are we going to be negative infinity, positive infinity, or does the limit not exist for each of these two questions? So if you want to work that out on your own, go for it. Don't forget you've got to factor the numerator, anything you can factor first before you can check all that out. And I'll jump to the solution. So there's the solution to your turn question. All right, so the first one is negative infinity, and the other one disagrees, so it doesn't exist. And we'll have a quick peek at the summary of things here. So it says sometimes we can evaluate the limit of a rational function that produces an indeterminate form, which we cannot evaluate it by simply factoring and simplifying. So we had nothing to cancel there, so we couldn't simplify. We were still getting indeterminate numbers. So such a function will typically approach infinitely large or infinitely small, or what we call negative numbers, as the values of x approach finite value from either side. So if we approach the same thing from both sides, like in this first statement, negative infinity, we get a limit that is negative infinity. And if both approach positive infinity, we say the limit is positive infinity. But if the right and left limits do not agree, we say the limit does not exist. So I hope that's helpful. Happy